Welcome to Eindhoven University of Technology and welcome to this MOOC on approximation algorithm. My name is Mark de Berg and I will be your teacher in this course. Approximation algorithms form an exciting topic in algorithms theory, and in this MOOC you will learn some of the basic techniques and concepts from this area. So, let's get started. In our first lesson on approximation algorithms, we're going to discuss some of the basic concepts. In particular, what is an optimization problem and why do we actually need approximation algorithms to solve approximation problems. Then we're going to formally define what a row approximation is, and this rho is the approximation ratio, which will be a very important concept in the analysis of approximation algorithms. So let's first look at an example. Suppose you have a server farm where you have a lot of compute servers. And now you get a number of computational tasks that you have to schedule on these machines. Of course, you want to do this in such a way that the time at which the last job, the last computational task is finished, is as early as possible. Let's look at a different problem. Suppose you go hiking. Okay, you go hiking and you don't want to carry more than 20 kilograms in your backpack. And there are many items that you may want to take on your trip. So what you can do is, for each of these items, you can assign a value to them. How much is it worth to you to take them on your trip? How valuable are they for you on your trip? And now you want to select a subset of these items such that the total weight of the subset is at most 20 kilograms and the total value of these items for you on your trip is maximized. So these are two optimization problems. In general, in an optimization problem, you have many different possible, feasible solutions. Okay, so for instance, for the backpack, for the tracking problem, any subset of items whose weight is at most 20 kilograms would be a valid solution. Okay? Out of all these valid solutions, you now want to take the best one. And that means that each of these valid solutions has a value associated to it, and you want to find the one with optimal value. And that can either be the solution with a minimal value, right? This would be if the value represents some kind of cost that you have to pay, or it could be the solution with a maximal value, in case the value represents some kind of profit. Okay, in practice there are lots and lots of problems that are of this type, that are optimization problems. Problems where you want to find either a solution that minimizes your cost or a solution that maximizes your profit. Unfortunately, many of these problems are very difficult, and in technical terms, they are NP-hard. Well, for us in this course, we're not going to look more formally at what NP-hard means, but for us it's enough to know that if a problem is NP-hard, then assuming P is not equal to NP, which is something that all computer science researchers believe to be the case, so then you cannot get a fast algorithm. Or more precisely, it's impossible to come up with an algorithm that always computes the optimal solution and does so in polynomial time. Okay, so if it's not possible to find an optimal solution in polynomial time, what can we do? Well, the first thing we could do is we could develop what is called the heuristic. Okay, this is simply an algorithm that gives you a valid solution, and where the value of this solution is typically close to the optimal value, hopefully. Right? And then you could implement and you could test and observe that in practice it performs pretty well most of the time. What we're interested in this course is something where we can prove something about the quality of our solutions. And that's where the concept of approximation algorithm comes in. So an approximation algorithm is an algorithm that comes with a guarantee how close the value of your solution is to the optimal value. Okay, so let's try to define this a little bit more formally. So an algorithm, let's call it alg, is an approximation algorithm if the following holds. Okay, so let's define alg of I to be the value that the algorithm computes, or the value of the solution it computes, I should say, when it gets an input I. And let's say that opt of I would be the optimal value for this particular instance. Right? And because our algorithm is an approximation, alg of I is typically not going to be the same as opt of I, it's going to be a little bit worse. Okay, so how can we quantify how good it is? Well, that's using the notion of row approximation. So alg is a row approximation algorithm, and here row is just a number. Let's say a 2 approximation, for instance, or a 1.5 approximation, if the following holds. And the definition I'm giving now is for minimization problems. Later, we're also going to look at what the definition would be for maximization. But for minimization, the criterion is that for any possible input instance I, the value of the solution that we compute, alg of I, is at most rho times the value of the optimal solution. Okay, and this value rho is called the approximation ratio. Okay, obviously, the approximation ratio for the minimization problem can never be smaller than 1, because it's impossible to compute a solution whose cost is smaller than the minimum possible cost. Okay, so this rho is at least 1, and actually, if it would be exactly equal to 1, you would always get the optimal solution. So for approximation, this rho would be bigger than 1. And hopefully it will be close to 1, and in that case, we have a very good approximation. So let's look at an example. In this load balancing problem, where we have to distribute jobs over machines, what is a 2 approximation algorithm? Well, it's an algorithm that computes a valid distribution, so it assigns all the jobs to one of the machines in such a way that the total time it takes until all the jobs are finished is at most 2 times the optimal, the minimal possible time. Okay, if we would have, instead of a 2 approximation, a 1.1 approximation, this would be even better, because now the total time it takes is at most 10% more than the optimal solution. Okay, let's do a little quiz to see if you understand the concept, the definition of row approximation. So suppose there's a professor, Professor Smart, who has designed an approximation algorithm for load balancing, and he claims that he has proved that this is a 2 approximation. Now there's a student who actually says, well, this algorithm is a 1.5 approximation. Okay, so is it the case that if the professor has really proved that this is a 2 approximation, that then the student must be wrong? Right? If it's a 2 approximation, it cannot be a 1.5 approximation. Or is it maybe the case that both can be right? That the professor has proved it's a 2 approximation, but the student, who claims that it's a 1.5 approximation, is also right. So the algorithm would be at the same time a 2 approximation and a 1.5 approximation algorithm. Okay, so think a little bit and try to remember the definition of row approximation. Okay, so the solution in this case is answer B. it could be that both the student and the professor are right. Why is this the case? Well, remember the definition of row approximation that says that the algorithm should be at most row times the optimal. So here, if it's a 2 approximation, then for any possible input instance, the value of the solution is at most 2 times the optimal value. Well, if it at most 2 times the optimal value, it could still be that it's always at most 1.5 times the optimal value. Because obviously if it's at most 1.5 times the optimal, it's also at most 2 times the optimal. So it's very well possible that both the student and the professor are right. Okay, now that we understand the definition of row approximation for minimization problems, let's have a look at maximization. Okay, for maximization, what do we have to change in the definition? Well, for maximization, we want to compute something that has the largest possible value. So now, instead of saying that alg of I is at most row times opt, we want to say that it's at least row times opt. Okay, and that also means that this value of row, which for a minimization problem is bigger than 1, would now be smaller than 1. Okay, let's look at an example in our knapsack problem where we want to select a subset of the items of maximum value for us, such that the total weight is, well, let's say at most 20 kilograms. Then what is a 0.5 approximation? Well, it's an algorithm that computes a solution, that computes a solution whose value is always at least 50% of the maximum possible value. If we would have a 0.9 approximation, however, then what we have is something that is always at least 90% of the optimal value. And obviously, this would be much nicer. Okay, so let's summarize. So what we've seen is what are optimization problems, right? Why do we actually need to work with approximation algorithms? Well, because most of the time these optimization problems are NP-hard. And we've defined the concept of row approximation, and that formalizes how close to the optimal value our solution, the solution that our algorithm computes, is guaranteed to be. Next lessons, we're going to see some examples of approximation algorithms, and we're going to see how to analyze them, look at some special techniques that we can use to design them, and so on.